Welcome to this 9th week of online lectures. I hope you're surviving well. Today, we will continue our exploration of techniques for online optimization, online or offline optimization. We will study MPCs. This has application to the OPF problem and to the next topic, which will be demand response. Your job for this week after the lecture is to finish the lab on OPF, which is due Thursday. To fortify what you have learned in the lecture, you should do also an online quiz called the MPC quiz, which will be online later today. And on Friday, we will start the following lab that will apply the techniques we see today and we saw also last week to control problems related to OPF. And those are also the techniques that apply to demand response. For demand response, we will not have an in-depth lab, but the techniques are very similar, whether we do OPF or demand response. As usual, use the Moodle forum, the online chat for any questions you have now or later. So the topic is today a technique, model predictive control. Model predictive control is the most important technique that is used for controlling loads and also generators. So it applies both to OPF and to the demand response problem. But given the importance of it, we will do a special course on it today. It's very, very simple, as you will see, at least as far as we don't want to dig into some of corner cases. So let me start with a generic description of what model predictive control is. By the way, many of you probably have heard or even used model predictive control or even had a course. If so, then take it as a summary and a verification of what you've learned. Otherwise, we will see in this lecture everything you need to know about model predictive control. Model predictive control is a technique for providing a policy. We have seen last week that in order to adapt to uncertainties, we may want, instead of computing a set point for a generator, instead of this, we may want to compute a policy that can be implemented online. And we have seen linear policies that are called affine disturbance feedback policies. Model predictive control is an alternative to that. It's also providing a policy, but in a very different way. The method is based on the following. First, you assume you have a dynamic state description. You have a model that allows you to describe the system you're controlling. For example, the system we're controlling can be an electrical grid, or, as in the example I will give here, we want to control the heating system of a house. That's the topic of demand response. So we assume that there is a state that I will often call X. Now we want to compute a control, UT. So UT is, for example, the set point of a generator. In the case of a house, it will be the amount of power or the set point of the heat pump. And the disturbance, which is whatever nature does. In the previous week, we saw that the disturbance could be, in the case of a grid, the deviation from forecast for the loads or for the generation of solar panel or other distributed renewables. And the goal, again, is to find a control that will work well when we don't know in advance what the disturbance is. So the idea of model predictive control is the following, is based on those 3 steps. We do it at repeated times. So at every time t, time is discrete. We do it every so-and-so. And now, how often do we do it? It depends on the inertia of the system that we're controlling. If we're controlling a grid that has solar panels and we want to react very quickly to solar panel variations, we may need to do that every second or every few seconds. If we're controlling a heating system, the inertia of a heating system is huge, so we may want to do it every few minutes. So every time t, we observe the state, and we choose one control action. Then nature, we choose how we can choose the control action, we'll see in a minute. Then nature would choose a disturbance, and this will change the state. In the case of a grid, there is no real state other than storage. If there is a battery in the grid, like there will be in the next lab, then the state depends on what we have drawn from the battery or put into the battery, for example. And of course, what we draw, put out of the battery may depend also on the disturbance. So the new value of the state, as given here, is a function of everything. And then we assume that we pay a cost. The cost may be the true cost that we're interested in. For example, if we are controlling the heating system of a building, the cost is how much we pay for buying this energy. So it may be a true cost. Very often we will see that we add to costs things that we call soft constraints or penalty functions that are a way to simplify, ease the job of the control by putting some of the constraints into the cost. We'll see that in a minute. And our goal is to minimize the integral of the cost over some long period of time. So that is similar to the dispatch plan problem we have seen in the past weeks. We'll apply this to now the user side, the demand side of the system. And I'm taking here as example the heating of a residential building. I took David McKay's house because David McKay published all the details of his house in this document, Renewable Energy Without the Hot Air. That's a wonderful book if you're interested about renewable energy. It's a very, very easy book, much easier than the things we do in this course, but it gives a lot of very, very useful basic equations and numbers for everything you may want to care about. For example, if you want to do an MPC to control your house, you will find all the details in this book, including the values here. It's freely available online. McKay was a wonderful author, originally physicist who worked in information theory, unfortunately passed away a few years ago. He was a friend of EPFL. In this lecture, so we will assume we want to control the heat pump of this house. So to do this, we need an equation of the system that we are controlling. The system we're controlling is the house, and we're interested in the heating system. So the state is essentially the temperature. Here I will use this simplified model that gives a relation between the control, which is how much energy we buy and put into the heating system. So it's the set point of the heat pump, and the parameters of the house. When we put energy, heat into a house, what happens with this heat? Well, if the house is very well insulated, it will stay inside, but perfectly insulated houses don't exist, so there is always some leaks, which is captured approximately by a linear equation that is given by this term here. It is the amount of heat that dissipates is proportional to the difference between the temperature of the house, capital T, and the outside temperature, multiplied by a coefficient that's called the leakiness. dt is how much energy over an interval of duration dt goes out in this way. Then the second thing that happens to the heat we put into the house is that hopefully is used to increase the temperature. So by increasing the temperature, it goes into the materials that are inside the house, the air, but that's not very much material, essentially the walls, the furniture, the house itself. So this is captured by the inertia of the building. So if we put a lot of energy and the building has a lot of inertia, it will take a long time for the temperature to raise. If it has a lot of inertia and very good insulation, the leakiness is small, then once the temperature has reached a desirable value, we need to input very, very little amount of energy. This is a simplified model. It ignores two things. One, which is not very important and is often not completely disregarded, is the fact that the house is not a homogeneous system. There are multiple rooms, so the leakiness might be different for different rooms, Probably the rooms that are close to the roof leak more than those that are downstairs. So a correct model would have one state variable per room, or if rooms are large, per fraction of a room. And the other thing it ignores is the other exchange of energy, which are not due to leakiness or inertia or loss of thermal loss through the walls or the roof, which are due to irradiation, loss or gain of energy. If there is sunshine, some energy will come into the house. So there will be another additional term, which is the free energy you receive from the outside. And another thing that you lose, which is with a slightly different physical law, is the loss through irradiation. The loss through irradiation is usually negligible in these kind of temperatures, but the gain of energy through the sunshine is hopefully important. But this is disregarded here. It's easy to add, it just adds another disturbance. And this is motivated by the picture here, where on these days here there was not much sunshine. So if we apply this to our model, we cannot live very easily with continuous time equations, so we discretize everything, which again is justified because the inertia of the house is very large, so the temperature, the state varies very, very slowly. So a first order approximation of this continuous equation, which is an ODE, is simply given by this, the over a duration delta t, which would be, for example, 1 minute. This is what happens. The increase in temperature is simply the delta in the temperature here. And this is the leakiness, which is proportional to the time step delta t. So that gives us, if we put everything together, the new state. Remember, the state we're interested in is the temperature, so t at time t plus 1. I massage this equation to put on the left-hand side the new state, on the right-hand side the old state, the amount of temperature, which is my control, and the outside temperature, which is the disturbance. If the weather is very cold, then I will need to heat my house more. If it's less cold than anticipate, I would need to heat it less. So that's a disturbance that's provided by nature, not by us. So if we put all in this form, we have a simple linear state equation where the new state is a linear coefficient times the old state plus linear coefficients applied to the control and the disturbance. Most systems that we control efficiently must be linearized. So this is an example where it comes for free. We said that the principle here is also to minimize the cost. So what is the cost? Well, the cost is certainly the price of the energy that I buy. So it's the price at time t, PT, multiplied by the energy that I buy. Here I'm assuming I'm only buying energy. I have not put solar panels where I could resell. That is something else that we will do in the lab. But here I'm assuming the price depends on the time of the day. So it depends on time t here. This is an essential ingredient of the smart grid. We'll talk more about that next week. But essentially, in order to drive the demands to do things as is optimal for the grid, we expose the users to difference in prices. If the price is very expensive, that means the grid has a hard time producing all the energy that is required, or producing or transporting the energy that is required by everyone. So we would like users to consume less by signaling through a higher price. So that's the first and perhaps the only physically significant part of the price. Here we add a second element, which is a penalty function for deviations from the temperature being from the desired state. So I'm assuming here there's a minimum temperature and a maximum temperature. In Mackay's book, this is from 18 to 20 degrees. In Switzerland, it might be from 20 to 22 degrees, depending on your perception of comfort. And we say simply that there is no penalty if we are inside this band, and we put a penalty that we make linear to make sure our MPC will eventually be linear. So we put this penalty function here. We will need to discuss the slope. The slope here is the thing that will give more or less importance to this penalty function. That's a very important trick. Sometimes we need to do it, sometimes we don't want to do it. Essentially, the thing to know is that an optimization problem is always much easier to solve if the constraints are put in the penalty function. As you have seen already from the previous lab, the difficulty in optimization is having the constraints. It makes the problem more difficult to solve in the sense of writing the code that solves it. We need to do things like Lagrange, use Lagrange duality and so on. But also it makes it not more difficult to express, but also really more difficult. It may be that there is no solution if there are too many constraints. We've seen that last week when we looked at an OPF problem. We had a large uncertainty. We saw that the optimizer could not find a solution that satisfies all the constraints in the face of all the uncertainties. So that's a problem that often exists when we have very complex problems. If we put too many constraints, it may be that it's simply infeasible. So to avoid this, if some of the constraints are not really hard constraints, if, for example, the temperature is not between 19 and 21, but goes to 21.1, then the system will not collapse. So that is what we call a soft constraint. So such a constraint where we can exceptionally accept a violation without any major dysfunctioning of the system, then it's better to put them as soft constraints. Then here is really the code of how an MPC works. We do a loop, so we repeatedly do the following thing. We must run this loop during whenever we want to compute the next state xt. So that must run fairly fast in a matter of seconds. Then we will do nothing until we get more information. And for example, if we compute a new set point every 5 minutes, we will run the sequence of operations every 5 minutes. So at every execution of this round, we observe the current state. We obtain a prediction of the disturbances from now until all the future bounded by a horizon little h. So that's an essential thing. The MPC, the idea that's in the MPC is that we look into the future to take the decision now. So we must have a prediction. That's a constraint. It works well if having a prediction is not too complicated. But that's the essential ingredient, because being able to look ahead will give us much better control. For example, if you think about the affine disturbance feedback we saw last week, this doesn't know much of what will happen in the future, just no bounds. But it doesn't know, for example, that at a given point in time, we can have a fairly good forecast of the solar production. Not a very good one, but a fairly good one. We know, for example, at 8 o'clock in the evening, there is much less sun, and in September there is 0 sun, for example, whereas at 12 noon there is much more sun. Of course, this prediction may be wrong. It may be 20% or even 30% less than what we had predicted. There may be unanticipated clouds, but certainly in the evening there will not be any sunshine after the sun sets. So there is this first order information that is easy to capture, for example, in the case of solar panels. Same thing for temperature. We can have an idea that usually the night is cooler than the day. So we can have even a raw forecast, and that will help the MPC. In fact, MPC is good if what we want is to be able to look into the future and take decisions where we think it's better to have a look into the future. For example, if I am having a battery at home and I want to do self-consumption, I know that in the evening there will not be a lot of sun, and I know that there might be a lot of consumption in the evening because we cook, because perhaps we bring our electric bicycles and cars to be charged, so there will be a lot of demand and little sunshine. And this is easy to predict. We may be wrong once in a while, but most of the time it will be true. So if you know this, of course you will act on your battery based on this. For example, you will try to have your battery as full as possible before hitting the end of the afternoon. So you need to obtain a prediction. Once you have obtained a prediction, we compute a complete trajectories of all our controls over all the horizon that we've taken. While doing that, we assume that the predictions will be the true things. So we look into the future and we do as if the future will be the prediction. And we compute an entire trajectory. And then that gives us the control for only this time step. Then we implement this. Nature then reveals the disturbance, and the state becomes whatever is the result of all these things. Then 15 minutes or a few minutes later, at the next control interval, we will re-observe the current state, which will be the result of what we have controlled and nature, and we will do it again. I'm illustrating this on the control of a car. MPC is used everywhere. It's used in particular in controlling mechanical objects, so autonomous cars or automatically assisted driving systems use MPCs. For example, if the vision system of your car views the road here, then you can anticipate and you view also all the objects, including the cars coming in the reverse direction. And that you can use that to do a prediction. You know that those things, they don't move at the speed of light, for example. So if an object is here, it will stay in this region for some amount of time. So you can do a prediction. Based on this, if the horizon is here, also we see that the road is bending to the right, so we compute a trajectory, which gives us a number of set points here. So the green trajectory is the one that is computed by the MPC based on the forecast it is making of what will happen in the future and based on the state information it has now. Then, of course, what really happens is not equal to the forecast. First, because what is forecast is not exactly known. Also, typically, there is noise in the process model. The state equation that we have depend on the disturbance. The disturbance may be whatever happens here, but also the noise due to, for example, the fact that if I give a given torque to some of my actuators in my car, there is also some uncertainty about the friction, about the surface of the road, about a number of things that will make noise and the difference between what I thought would be and what will happen in reality. Another important source of noise is also typically that my model is oversimplified. A simplified model means that we have a model that makes things tractable. The reality of the system is, of course, usually more complex. So that disturbance reflects all of this. So at time t+1, the car will be somewhere else. Then what we will do, of course, we will not insist on going to those points. We consider them as invalid. We will compute a new trajectory and we will implement only the first point. And you might ask the question, why do you compute a full trajectory if you implement only the next point? Well, the idea is exactly looking into the future. I know I will need to take a turn to the right, so I know I need to go here. I cannot go outside the road either. So I need to do something that takes into account all the things that will happen later. But at every time step, I correct my forecast and the result of my actions by starting from observation, not from forecast. So we always look ahead to each time step, but we adapt to the uncertainty since the implemented action always incorporates the latest observation of the state. So in some sense, the MPC is essentially robust. It's not something that says, let me compute a trajectory, let me implement it and come back in 6 hours. No, we constantly compare the plan that we had done to the first step of its execution. So in that sense, it is robust here. There is a question on the chat about what is this epsilon thing here. Epsilon is one of the parameters of the model of the house. It's called the coefficient of efficiency. It means that if I inject if I buy from the grid some amount of electricity, UT, what I will pay is P times U. So U is what I buy. That's what I will read on my meter. The amount of heat that is injected into the house is not U of T. It's multiplied by coefficient of efficiency. If you have a old technology system, like a resistive system, then the coefficient of efficiency will be slightly less than 100%. A resistance is a very efficient system to dissipate heat. It's not very efficient. It's not a very good way to use electric energy, but it dissipates all the energy into heat. So it will be a little less than 100% for a resistance. If you have a heat pump, it's more efficient because, as you know, a heat pump is extracting heat from the environment. So if you give 1 watt hour to a heat pump, it will put into the house more than 1 watt hour, depending on the number of elements. Depending on the technology of the heat pump, it will be between 2 and 3. So this is the multiplier that we apply to the energy. That's the net thing that is input into the house. So let's apply this MPC generic technique to our house. So the disturbance is the outside temperature. So we will need a prediction of the outside temperature. Here we don't need to be very accurate. What is most of the time done in systems that do control heating system is to simply look at time series of the past year. So you look at the average of the last 3 years on the same day of the year, and you will take this as your forecast here. Then the cost that we're minimizing, as we said before, is the monetary cost of the energy plus the penalty function. So that will give us a sum of these costs over the entire horizon. Subject to the constraints. What are the constraints? The constraints on my control are here. I can put any amount of energy here between 0 and Umax. So this is assuming a very modern heat pump where you can vary every minute the set point. Some other heat pumps are less flexible. There may be ramping constraints. There may be discrete values. So you would have more constraints here. And also the constraints are the state equations. So the state at time t+1 is given by those linear equations that capture the thermal model of the house. This is how the temperature will vary when we apply this control. And of course, we need the state because the state here appears in the cost function. As mentioned, we use soft constraints. An alternative would have been to say the cost function is only this term, and then we would have added constraints on the temperatures that they must be between Tmin and Tmax. This would also have been possible, but it would take the risk that the control is a bit less good because we put more constraints. MPC style means we do the following. At every time we observe the house temperature, so the control system, every 5 minutes, for example, reads the house temperature, solves this optimization problem. So hopefully it won't take many, many minutes to solve it. So that must be done in a matter of seconds. And this returns the set point for the heat pump, U of t, which is then implemented. And then you sleep for 5 minutes, then you observe again the house temperature and you implement a new set point here. This is what I did, at least in a simulated model of the house here in MATLAB. You see that I did it over a period of 2 days. The horizon was also 2 days, if I remember well. And I'm showing here several curves. I'm showing here the room temperature. Here the dead band is between 19 and 21 degrees. We see here that the soft constraint was very successful. The room temperature was never outside the bands. I'm showing here also the forecast. So the forecast is the smooth dotted line here. As you can see, it's not very fancy. And the true temperature varies from the forecast. The second day was above, and the first day it was fairly closely matching the forecast. And this orange curve here is the price of electricity. So this is assumed to be known. In some systems, the price is revealed at the last minute, but that's a bit nasty. So here we assume the prices are known. So we see there are low price periods, which are during the night, and also here during lunch. This is because there is probably solar energy in this grid. So there is a lot of solar energy just before lunch. Perhaps during lunch, there is a lot of demand. So the operator of this grid provides those prices here. And then during the day, the prices are medium, and there's a peak in the prices at the peak periods of the morning and the evening, when there is no solar production and there is a lot of human activity. So those are the peak prices. And we see what the MPC has computed. We don't see exactly the value of U, of the control, but we see the result on the temperature. And we see here that what the MPC has done, it has started heating the room. So here I'm assuming a simplification also, that the room temperature target is the same day and night. So we have a very, very conservative person who wants her house to be warm also at night. In practice, of course, during the night, you would like the room temperature to be also lower. Here we see that the room temperature was 90 degrees in the middle of the night, and then the heating system is starting heating it to the maximum temperature of 21. And why did it do that? Well, because it was anticipating that there would be a period of high price coming here. So it wanted to not heat the house during this period. Because the house is not perfectly insulated, there is some leakage. So we need to provide some heat to the house always. But here we will not provide any heat. In fact, you see, this is in fact an exponential decrease here. We see that the house is cooling down. It's left to itself, so no heat is injected. So that is a natural decay of temperature. So what the MPC has done, it has decided to heat the house before the high price period, let it go down until it reaches a period here where prices are again very low. So it will heat again, let it drop, and etc. So this is what the MPC will do. And it is in fact providing a response of the house to the desires of the grid operator. By exporting prices here, we have incentivized the house to heat before the peak period and to not heat during the peak period here. That's a form of demand response by price here, which is very effective. The cost here will be less than if we had done something that is not controlling through an MPC. Those are the temperatures I used for this house. They are the temperatures, those values are the parameters, sorry, no, the parameters are taken from Mackay's book, from his own house. And this is the kind of things that a thermal engineer will do if you are designing the heating system of a building. For example, at EPFL, we have several buildings that are controlled using such systems. Here, this is the penalty function that I added. A penalty function is a bit tricky. You need to compute a magic number, which is the weight. Here, I put a weight of 1, which has to be comparable to the rest of the cost. That means I considered 1 franc of penalty per degree of violation per minute. So in some things, it's a huge cost. And we see that the effect was that the constraints were always satisfied because the cost of the penalty is very large here. Here I can compare to what we do if we don't have an intelligent heating system. If I have simply a thermostat that I set to 19 degrees, which is the middle of the deadband between, at 19 degrees here, then we see that the thermostat will heat until it reaches some epsilon above the band that it's controlling. Then it will drop heating, then start again. So it will be on off, and it will provide this quasi-constant temperature. But of course, it completely ignores the fact that there's a period of the day where heating was very expensive. And this turns out here in the price, we will see that we are significantly more expensive. We're not adapting, so the thing is completely myopic. This is the state of most heating systems today. In a smart grid, we would like to control the things that can be controlled through MPCs typically. We see that the MPC does a forecast, but it also adapts to the deviations from forecast. So if you look at the room temperature here, you see that the curve is slightly different here. So the MPC has reacted slightly to the fact that here, for example, the temperature is much larger. So I re-emphasize this, that an MPC is really adaptive, of course, as any policy must be, but in some sense it has some inherent level of robustness. Even if the forecast is very different, it will sense that the forecast was different because the inside temperature will be higher than given by the model according to the forecast. Voila, so this is the easy part of the story. So what I've shown here is how I write an MPC, this one, and how I solve it. Now, we can't simply ask MATLAB to solve it because there are too many little steps that need to be done. And this is what we will do in the rest of, in section 2 here. We will see how to get rid of all the little details. We have started doing this already in the past weeks. We have seen that very often we make things piecewise linear. I mean, the graal of optimization is when everything is linear, but that is too restrictive. So we can deviate from linear by having things that are convex, but piecewise linear, and how to rewrite problems when there are such complexities in them. So we will not see how to solve problems that have quadratic objectives, for example. That is a topic of its own. But we will focus on the problem rewriting rules, which is, for the practitioner, the most important thing we're confronted with. We have seen that already. We've seen the max removal transformation. In fact, we will see today a more generic set of transformations that will help us a lot. But before getting there, we need to make sure we are comfortable with max and min. We will often see in our objectives and or sometimes in our constraints, min and max. So we need to make sure we are well comfortable and avoid some of the mistakes that can easily be done. For example, so here is a little quiz. I'm assuming I have a function or an optimization problem, if you want, that consists in saying, first, I have a function of two variables, x and y, and the constraints on x and y are very simple. They are independent. There's a constraint on y and a constraint on x. There is no joint constraint on the combination of x and y. So that's a simple thing. So I first maximize the function with respect to y, then I take the mean with respect to x. Or I do the other way around. I minimize first with respect to x, and then I maximize. Say what will happen. So the quiz should be open on Speak Up. I close the poll in 5 seconds. And the majority says B, which is quite tempting, but this is not true. So that's why we do this little drill on min and max, because it's easy to get confused. This is not true, because it's so easy to get confused, and that's a fundamental inequality in all of optimization theory. It's not the main focus of this course, but we are confronted with this, so to avoid falling into some of the traps, let's go through this. Here, let me illustrate this on this chessboard here. Assume I want to minimize a function of two variables. X is here, it's the index of a column. Y is the y-axis, so it's the index of a row on a matrix. And f of x, y is the weight of an animal that is at position x and y. And assume that on my chessboard I have mice and elephants. And assume, to simplify the story, but this is true even if this assumption is not true, I'm assuming, to simplify the story, that there is one animal of each type on every row and every column. So if we do this and we look at what is the first thing, we take the minimum over x first. Well, that means that on every row, we fix y and we take the minimum on this row. we obtain the weight of the smallest animal, which is always a mouse. So we take the minimum first, we obtain always a mouse. And then we take the max. Then we obtain the max weight of any mouse. So the biggest mouse that happened to be the smallest animal on its row, but is now the biggest among all this short list of mice here. So our B star, the max of the mean, is the weight of a mouse. If I do the same by changing the order, I fix x1 and I took the max over y. So over the first column, what is the largest animal? It's the largest elephant, and I always obtain an elephant, small or large, depending on the size of the largest element. And then I take the mean of all these. I obtain the weight of the smallest of these elephants. So we obtain mean of max, that's the weight of a max. A max was always an elephant, a mean of max. So the smallest elephant that was chosen was the max of mean is the biggest of the mice. Now I assume a mouse is always even big, is smaller than an elephant, even if the elephant is small. So we see that A star will always be larger than B star. And this is true for any situation. If you minimize f of x by if you take first the minimum over x and then the max over y, and there are no joint constraints here, it's always in that sense here. This is called the max-mean inequality. Well, we will not use very much the max-mean inequality, but the take-home message is, well, we should not confuse this and believe that interchanging the order of mean and max is irrelevant. In fact, it matters. In general, in quasi all cases, there is a strict inequality, as in the example I gave here. There are cases where there is not there is inequality, but those are really special cases. For example, if you remember, we talked about duality. We can interpret the duality result exactly in this sense. If I have an optimization problem, remember that the dual function is obtained by compute is the minimum over x of the unconstrained problem, which is the Lagrangian, the minimum of the Lagrangian. And if we take the max over this, that gives us the objective function of the dual problem. Now, it's not immediately obvious, but once you know what you have to show, it's very easy to show that, in fact, the primal problem, the original optimization problem, which is minimizing the objective f of x subject to the constraints on x, is the same as minimizing the max of the Lagrangian. Therefore, and that's very easy, there's no rocket science here, that's just looking at the conditions that can happen here. So the primal objective is a mean of max. And the constraints, that's the beauty of duality, are there's no joint constraint here. Here we have constraints on the Lagrange multiplier, and we have the domain of definition. So we have removed the joint constraints on x here that were in the original problem. So it can be shown that this is the same as that, and minimax equality simply is the weak duality. We know that in general there is a duality gap, except when problems are convex and satisfy strong constraint qualification, in which case there is equality, but again, those are very special case, and you need special conditions for this to happen. It's very special, though we use it very often, but in general, if you take a mean and a max, you will not have this equality. So we saw that combining mean and max is risky. Combining mean and mean, or is it equally risky? So second quiz of the day. How about this one? I close the poll in a few seconds. and the majority says B, which is correct. So here, there is no trap. If we think of mouse, then it's easy to see. C star is obtained by first selecting the smallest mouse on every row, then selecting the smallest of the smallest. So that will give you the overall smaller. So if you want to choose what is the smaller object in a large class of objects, you can, in a large collection of objects, you can first subdivide the collection into small bags of objects, take the smallest in every bag, and then the smallest of all the resulting smallest will give you the overall best. So that's the divide and conquer. Well, this is what every competition does. So that works. So the take-home message is here, there's no problem. There's even more than that. We can interchange the order, but we can also interpret this as the overall max. So there are two interpretations of this result. The order doesn't matter, but also what we do when we do this thing here is finding the overall max. So it is min, sorry, not max, min. This property is called associativity of min. This is analog to what we do when we have integrals. If you have to imagine here, this min is an integration. You integrate a function of two variables over a set X, then you can interchange the order. And what you obtain is the integral over the two-dimensional function here. So this is exactly the same. Of course, the same is, which is true for min, also is true for max. So take-home message, we can mix and match mins, we can mix and match maxes, but mins and matches and maxes are like cats and dogs, they don't live well together. Voilà, I think we will do a break now, 10 o'clock. So we will stop here and resume at 10:15.